Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome back. So, we have been discussing about Reynolds average Navier-Stokes equations, and we saw what are the different kind of turbulence models and where we can use them, what are the limitations of the turbulence models, and what are the situations where we cannot be sure of the results from the range or the turbulence models. So, in those cases we need to go to some high resolution simulations. Okay. For example, we have been discussing about the large eddy simulation, okay, which is LES, okay, and also we have been discussing about the direct numerical simulation, which is DNS. Okay. So, we have primarily three methods of simulating a fluid. One is the Reynolds average Navier-Stokes. We have studied a great deal about it. Okay. In the next few lectures, we are going to see how we can perform LES and DNS and what are the practical considerations when we are using or performing LES or DNS. Okay. So, one thing that we have discussed so many times is that compared to range, the LES and DNS are very expensive, right, and one primary reason is that in Reynolds average Navier-Stokes equations or in the range simulations, we solve for the average quantity and we do not get the fluctuating quantity, we model the fluctuating quantity. So, we can have different kind of models, we can have the model which basically gives you the final output of turbulence kinetic energy or the dissipation rate or the specific dissipation rate. So, like we have K epsilon model, K omega model, SST K omega model, and then there are models which are based on stresses directly also, computation of stresses directly, which are the Reynolds stress models, okay, which are not the eddy viscosity models. So, because we are only interested in the mean flow, so we need not go into the finary scales of basically finding out the exact turbulence quantities, but if a statistical value of the turbulence quantity we get, that is good enough if we are doing for the mean flow. On the other hand is the DNS, which is the direct numerical simulation, and as the name indicates, we are going to simulate the flow as it is numerically. Okay. We are not going to employ any model, okay, that is why it is called the direct numerical simulation. And because we are simulating it directly, we need to resolve all the scales of the turbulent flow, and that is why it is very expensive. And today we will see that what are the expense that we are talking about, like let us say we are doing range and the DNS. So, what is the computational cost that is going to increase when we shift from range to DNS. So, we will look about that very shortly. In between you have LES, okay, and if you recall the diagram that we have discussed some time back, that in DNS we do not model any scale, okay, we just simulate everything. In Reynolds we may model the entire turbulence, okay, and LES we basically if you talk in terms of eddies, we know that turbulence flow is made of large eddies and small eddies. So, in LES we simulate the large eddies, but we model very small eddies, okay. And there are multiple versions of LES also, there are wall model LES, there are very large LES, okay. Then there are hybrid methods of doing LES like hybrid range LES approach, okay. There is whale model, okay. So, there are many variants of LES also, okay. We will not go into those variants of LES into great detail, but we would rather see that what do we mean when we perform LES, okay. And we once you have the physical picture of what we are trying to do using LES, we can actually based on your interest you can go and look into different kind of LES models. So, if you look at this picture, okay, this is a jet flow, okay, and you can find I mean this is a turbulent jet flow as you can clearly see, and you can find different kind of scales in this flow. you can have very small eddies. Okay, you can, for example, you can see here there is a very small eddy, and then you have this eddy, and you have many different scales. Okay, you have very small eddies like here, like here. Okay, and in order to resolve this entire flow field, you need to have grids which can, for example, resolve this also, and you can resolve this entire big flow field also, right. So, you have a variety of eddies, and you basically when we say eddy, we have a picture of like this in mind, okay, but it's a kind of flow which has got some kind of vorticity, right, and you can have large eddy and the small eddy, but it's very difficult to basically identify or basically segregate a large eddy from very small eddy, because these all different scales are mixed up, okay. But in order to capture very small flow features, okay, which are very fine features, we need to have that kind of grid, only then we can capture that, right. So, look at any turbulent flow, this is random, the turbulent flow is random, it is unorganized, and despite being random, it has got some kind of statistical properties, okay. It is chaotic, and it has got multiple scale, okay. So, we can have very small scale to very large scale. Let us take the example of boundary layer, for example. Okay, so, you can have something which is happening very close to the wall, okay, very close to the wall, let us say here, and then you can have something which is of the scale of this. Okay. Similarly, you can have, let us say you flow inside a channel. Okay. So, this is your large scale phenomena, and then you have something inside the boundary layer. Okay. So, you have to basically resolve both the smallest scale as well as the largest scale. If you talk, let us say in terms of atmospheric boundary layer. Okay. So, this is, let us say this is your big atmosphere. Okay. So, you have to basically resolve, it can go to the kilometers, okay. And then from the ground to the level where the ground effects are not very important. So, I am talking about that domain. So, that can go up to kilometers. On the other hand, you can have few meters or centimeters, which is very close to the boundary layer. So, both phenomena are important. So, if you want to, let us say, resolve this atmospheric boundary layer using a direct numerical simulation, you need to have a grid which is basically very small in size, which can capture the boundary layer very close to the earth, and it can also capture the effects of the earth outside. Okay. So, this is one example. I think we have seen this earlier also. So, we have got a mean flow. I mean, this is a typical picture of a turbulent flow, where you can basically divide your any flow field into a mean flow and a, let us say, fluctuating quantity. Okay. So, this mean flow imparts energy, okay, to the eddies, and you have large eddies. So, these are basically large eddies, okay, and these are very small eddies. Okay. So, remember that famous Richardson poem, that the large eddies impart energy to the next level of eddies, and then they will basically impart energy to the next one, and so on and so forth, till they go to the smallest scale, and when it goes to the smallest eddy, okay, that is where the dissipation takes place, right. So, it is an entire cascade, okay, from the very large eddies to very small eddies. So, here what is important is the dissipation, right, because here the viscosity basically plays a big role, and here what is important is the production, because these eddies get energy from the mean flow, and in between you will have the transfer of energy. So, same thing if you see in terms of the energy cascade, right. So, what you see here is wave number. So, k is the wave number here. Okay. This is not the turbulence kinetic energy. Okay. So, this wave number can be related to the inverse of the eddy size. So, if you have a eddy size, let us say this is your eddy size, typical eddy size, whose length is, let us say, L. So, then wave number could be written as 2 pi by L L. Okay. So, if the wave number is increasing, then your eddy size is decreasing. So, this is very large eddy, this side if you see, this is very large eddies, and this side basically small eddies, right. Now, what you see in the y axis is basically the turbulence kinetic energy density. It is not the kinetic energy, but the kinetic energy density. That means, if you take the area under the curve, this entire thing, this will give you the entire kinetic energy, right, and this is plotted in the log scale. Okay. And why it is plotted in log scale? So that you can find some slope here, and this slope has got some meaning. Okay. If you have attended any course in turbulence, you know that this slope is around minus 5/3 and so on and so forth, right. So, when you plot in log scale, it will be a straight line, right. So, this is the large eddy and then this is the smallest eddy, right, and you can see this this large eddy is represented by a length scale L and the smallest eddy is represented by length scale eta. So, right, what happens is that in this region, for example, let us say somewhere around here up to this point, the production is important, okay, and after this, let us say the dissipation is important, and in between is the transfer of energy. Okay. So, in the region where the production is important, what are the quantities that are important is your turbulence kinetic energy and the dissipation rate, right. And where there is a dissipation of energy, what is important is your viscosity, because the dissipation is happening due to the viscosity, right, as well as your dissipation. And in between, where there is a transfer of energy, what is important is the length scale L and the dissipation of energy, right. Now, what is our interest, why we are discussing this in detail, and this will be coming to this picture again and again, because this is the crux of the matter which differentiates your RANS to DNS and LES. Okay. In RANS, you will not see this diagram, because we do not segregate the turbulence kinetic energy based on the wave number or the eddy size. Okay. We basically model it, we basically model, so I will call it Ke, because for the turbulence kinetic energy also we use the same symbol as K. So, in order to avoid any confusion, I will call it TKE. Okay. Let us call it TKE. So, in the RANS simulations, okay, we directly model TKE and we do not segregate based on the wave number. So, we cannot get this picture, but what we can get is the entire integrated quantity of this diagram, right. On the other hand, when we do LES or DNS, so when you do DNS, you will get this entire spectrum. Okay. If you have a well resolved DNS, we should get a picture like this, we should get this 5/3 curve, we should get the dissipation range, and we should get this integral range. Okay. When you have LES, so that is somewhere in between. Okay. So, LES, what you can do, you can argue that okay, I do not have that much computational resources to simulate the entire scale, and I am not very much interested in what is happening at very small scale, right. So, your scales at which the dissipation is happening may be not that important to basically capture your mean flow dynamics, right, or even the some of the unsteady dynamics. So, what you can do is that you can model this part. Let us say you can argue that okay, I am going to model everything which is right of this. Okay, I am going to basically capture my inertial scale, which is the inertial range is on here on the integral range, but very small scales. Remember, when as we go to the smaller and smaller or the finer and finer grid size, that is where the computational cost increases, right. So, let us say I have something of 100 meter, and then let us say I have something of 10⁻⁴ meter, right. So, what is the grid size? So, if this is my 100 meter and my minimum size is 10⁻⁴ meter, let us say in this side or this side. So, the grid size is, if you consider a uniform grid, is 10⁻⁶, right. You will have 10⁻⁶ number of cells, right, in one direction, right. So, if you decrease this value, let us say you want to go to a scale which is 10⁻⁶ meter, where your dissipation is happening, right. So, in the same, if you go follow the same argument, this will go to 10⁸, right. That many number of elements you will need to have if you want to go to this scale, right. Let us say that your all the things that is happening, the important events or important phenomena that is happening could be captured by this by scale which is up to 10⁻⁴ meter, which let us say somewhere fall here, okay, which remember the wave number is inverse of this scale. Okay. So, then what you can do that between 10 to the power minus 4 and 10 to the power minus 6 you could use some kind of model. Okay. What the model does? It basically ensures that whatever thing which is coming on the right of this is dissipated. Okay. So, that is why your models like SGS model, which is called the subgrid scale model, or there are some LES which is called implicit LES that takes care of this dissipation by actually considering a flux scheme which has the dissipation inbuilt, or you can have some kind of filter. Okay. But essential idea is that you capture the initial inertial range to the extent possible and the integral range, but model the dissipative range. Okay. That is what we do in LES. Okay. So, you will get a basically cascade up to the dissipative range, before the dissipative range, and after that it is model. You will not get the, you will have the energy drop suddenly at this point. Okay. So, now let us find out that what is the kind of number that we are talking about when we say that we want to resolve all the scale, right. Let us say you want to do a DNS. So, what is the kind of numbers you are talking about depending on Reynolds number. So, what is the quantity that is basically dictating the flow in most of the fluid flow is the Reynolds number, right, which is some kind of density scale, velocity scale, length scale and your viscosity scale, right. So, for this Reynolds number, let us say if I say that my Reynolds number on a wing, because we have taken many examples for aerodynamics, take another example. So, let us say flow over a wing is happening at Reynolds number of 10 to the power 6 or 1 million, let us say on a based on the incoming flow and the chord length or mean aerodynamic chord of the wing, right. So, this is the scale. So, the question is that if I want to do DNS of this wing, what is the number of grid size, number of grid points or the grid size that we are talking about, right. And it so happens that you can basically make some scaling argument to get into some approximate numbers. Of course, that will not be a definitive number, but you will know that what is the range of scale that we are talking about, you will know the ballpark figure. And this was beautifully given by Kolmogorov, okay, who basically made some argument and made some assumptions and came up with a number which can be basically directly evaluated based on your Reynolds number. So, what we are going to do in that? So, we will define two eddies. Okay. If you go to the last picture, so we will have the large eddy. Okay, let us say here. Okay, we have the very small eddy. Okay. So, we will take these two eddies and we will say that the production is happening with the large eddies and dissipation is happening at the smallest eddy. Okay. And they will make some connection between the two and try to find out one number of the average grid size. Okay. So, what I am doing here, I am defining the largest eddy with the length scale L, okay, and it has at the velocity scale which is u. Okay. And for the smallest scale, smallest eddies which are responsible for the dissipation, we take the length scale as eta, okay, and we take the velocity scale as v, right. Now, we are going to look at the two extremes of the spectrum. One is the production where the energy is taken by the largest scale from the mean flow, and another side is where the dissipation is happening due to the smallest eddies, right. So, this is my diagram, okay. This is my E k versus k, right, and this is on the log scale. Okay. Okay. So, what we are saying that for the largest scale, let us say somewhere here, what is the rate of production of kinetic energy, right. So, of course, the kinetic energy is half m and u square, and then the rate of production of kinetic energy, right, per unit mass, that is m, and then rate, because it is rate, this is t, right, and forget about, so let us call it the production. Okay. This is rate of production of kinetic energy, which is happening due to the largest eddies, right. M will cancel out, and T you can define, because we have defined the length scale and the velocity scale. So, we can define the time scale also. So, time scale will be length by velocity. Length is meter, velocity meter per second, right. So, that will give you the second, right. So, this will become this will be of order of u square by L by u, which is basically u q by L, right. So, this is what is written here. Okay. Now, let us look at the dissipation, which is another extreme here. Okay. So, what is the rate of dissipation? Now, there are multiple ways to arrive at it. Okay. What we are going to discuss is that what we have done in the RANS modeling also. So, the dissipation is given by viscosity Eij, right, and this is the velocity tensor. Okay, we have been discussing so many times, and this is nothing but depends on the velocity gradient. So, if you go by the basically a dimensionality argument, so this will be nu, okay, this is viscosity, and what is the velocity gradient for the smallest scale. So, we have the velocity scale which is small v, and then length scale is eta. So, that will be v by eta, right, v into v by eta. Okay. Do not get confused. So, nu is like this and v is like this. Okay. So, that will be square. So, you have nu v square by eta square. So, that is the rate of dissipation, right. Now, what Kolmogorov did, he made two assumptions, and those are very fair assumptions. Okay. One is that at any time in equilibrium, for equilibrium to turbulent flow, the production, the rate of production of kinetic energy is equivalent or similar to basically the rate of dissipation, right. So, basically the production is like dissipation. Okay. So, you can say that u q by L, which we derived here, is equal to nu v square by eta square, right. This goes as nu v square by eta square, right. Remember what we have started with, we want to find out what is the smallest scale that we need to resolve based on a given condition, let us say the Reynolds number, right. So, this does not give you the enough information. Okay. It relates the largest eddy to the smallest eddy in some sense, in the sense that if you know the largest velocity scale and the length scale, you can relate it to the smallest velocity scale and the length scale, right. But we want something on the gross parameter like Reynolds number. So, then the another argument that Kolmogorov made is that at the very smallest scale level, which is scale of v, okay, the viscous forces and the inertial forces are comparable. Okay. What does it mean? Is that Reynolds number at that scale is equal to 1. So, remember, if the inertial forces are basically very high, then dissipation will not happen, right, because the things are getting dissipated at a very fast scale at the smallest eddy level. So, that is why we argue that the viscous forces are very at least comparable to the inertial forces, and as we know that Reynolds number is a ratio of inertial to the viscous force, right. So, that means the Reynolds number at that scale is equal to 1. So, that means v eta by nu is equal to 1, right. So, that way we can say that v is equal to nu by eta, right. So, we related our velocity to the viscosity and the length scale of the smallest eddy. Now, if you use the second assumption, which is basically v equal to nu by eta, and we know the what is the dissipation rate. Okay, what is the dissipation rate? Is v nu v square by eta square, right. So, if you use that argument, epsilon equal to nu V square by eta square, and we have discussed that V equal to nu by eta. So, you can replace that V thing. Okay. So, the viscosity and then V will be replaced by nu by eta square by eta square, right. So, that will become nu q by eta to the power 4, right. So, the epsilon is nu q by eta to the power 4, and that way you can find out eta is equal to nu q by epsilon to the power 1 by 4. Okay. So, we found out. So, what is nu? This is basically the smallest eddy size, this which we want to resolve. So, we actually related it to the viscosity, okay, but there is another parameter which is dissipation rate, and it is not easy to basically find out the dissipation rate. Okay. So, what we are going to do now, we will use the first assumption as well. Okay. And what is the first assumption? The production is basically very similar to the dissipation, right. So, then u q by L is nu V square by eta square, replace this V with nu by eta. Okay. So, that is nu by eta square by eta square, right, which will become nu q by eta to the power 4. Okay. Now, we are going to do something here. Okay. So, we are going to rearrange some of these variables. Okay, I am going to write it on the top. Okay. So, we have u q by L, which is going as nu cube by eta to the power 4, right. So, I will rearrange it. So, this is eta to the power 4 by L is equal to nu cube by u cube, right. I am going to multiply L cube on both the sides, right. So, that will become eta nu by L to the power 4 is proportional to nu by u L cube, right. So, this is like your largest eddy velocity, largest eddy size. So, what is the largest eddy velocity and size? So, this you can relate it to, let us say if you have a flow inside a channel, right. So, your eddy will be of this size, right. So, this is your largest eddy size, right, for example, right. And typically you define the Reynolds number on these kind of scales. The so if you want to define a Reynolds number here, so R will be u L by nu, right, and u is something like somewhere here, right, at the mean flow at the center line, right. So, if you use that definition, you have eta by L to the power 4 is proportional to 1 by R e to the power q, right. And then going ahead, you will have eta by L is basically proportional to R e to the power minus 3 by 4, right. So, your this is the scale of the smallest eddy to the largest eddy, right. So, now what we have done, we have related the smallest eddy size to the largest eddy size with the Reynolds number, right. So, if you know the Reynolds number, we know, and we know the let us say your geometry size, let us say here the L is given, you can calculate the eta, which is basically L R e to the power minus 3 by 4, right. So, in the next class we will see some examples that when we have different kind of Reynolds number, what is the kind of grid size we are getting when we want to resolve the smallest scale to the largest scale. Okay. So, we will stop here. Thank you.